All right, welcome back. And here we are at the final question on the 2012 Cimc competition. Final question in part B. So it's going to be a written question. And it's a bit of a long one, at least in terms of its setup. So let's get into it. Vernon starts with a first number n, with n between 0 and 1, non-inclusive. Okay. Vernon enters the first number into a machine to produce a second number. He then enters the second number back into the machine to produce a third number, and so on and so on. And this gives us a chain of numbers. So when Vernon enters a number x into the machine, we have two possibilities. If x is a half or less, the machine outputs 2 times the given input number, 2 times x. If the value that we put into the machine, x, is greater than a half, strictly greater, the machine outputs 2 times 1 minus x. So the difference between 1 and x times 2. If the machine ever produces the number 1, Vernon stops the process. Okay. Anytime we see a 1, we're done. So, question A, or part A, I guess. A chain starts with 3 elevenths. This gives 3 elevenths, then the second number will be 6 elevenths, then the next number will be 10 elevenths, then down to 2 elevenths. Okay, so this is giving us a little time to verify that we understand how the machine works. So 3 elevenths, that's less than a half, so our machine should output 2 times that. 2 times 3 elevenths is 6 elevenths. Okay, that makes sense. So what are the next 4 numbers in this chain? So basically we have to start with 2 elevenths and figure out the next 4 numbers. All right. So let's figure things out. So, starting with 2 elevenths. Now 2 elevenths is less than or equal to a half. Okay, not rocket science. So the rules of the machine tell us that it outputs 2 times the number we put in. So 2 times 2 elevenths, that's going to be 4 elevenths. So that's the next number in the sequence. We figured out the first number of our sequence, of our chain of 4. Now 4 elevenths is still it's still less than a half. It's strictly less than a half. So once again, the machine's just going to double it. So 2 times the input. Alright, so now our chain looks like 4 elevenths, 8 elevenths. Where are we going next? Right. Now 8 elevenths is greater than a half. So what does the machine do? Well, it doesn't double the number. It does 2 times 1 minus the input. Okay? So what's that? Okay? So that's 2 times 3 elevenths, which is 6 elevenths. And if memory serves, I think that was a number we already saw in the sequence. So we could go back and check, but it doesn't really matter. We just need to figure out one more. So 6 elevenths, that's also greater than a half. Two times 1 minus 6 elevenths, Well, that's going to be 2 times 5/11. That's going to be 10 over 11. And we're going to write the next 4 numbers in the same notation that they gave to us. Okay, so that's 4/11 goes to 8/11 goes to 6/11 goes to 10/11. Right, and that concludes question 1. We've got the next 4 numbers in that particular chain. B part. Vernon enters a number x, and it's between 0 and 1. And he enters it into the machine, and the machine returns that same number back to him. Determine this value. Okay. Sounds straightforward enough. So when we enter x, we have 2 possibilities. So, using their notation, we have x goes to x. So we have 2 possibilities. If the number we put in is less than or equal to a half, but of course, if we double a number, it can't be equal to itself unless x is 0. And that's impossible because we said that 0 is less than x, less than 1. So that can't happen. So that's definitely not the case. So what does that tell us? Our x value has to be greater than a half. The other possibility. Okay, so we got 2 times 1 minus x. But we know that this is just going to be the same value of x again. We put x into the number and it spit x back out. So we can equate x and 2 times 1 minus x. So that's 2 minus 2x. Much nicer way of writing it. So we have an x over here, we have minus 2x over here. Let's bring those x's over to the left-hand side. And so the only possibility we're left with is that x is the value of 2/3. So let's check. We plug in 2/3 into our machine. Well, that is greater than a half. Okay. That makes sense. So what does our machine tell us to do? It tells us to double the difference between our number and 1. So 1 minus 2/3, that's a third. 2 times a third, that's 2/3. So we got 2/3 back. So we've done a little bit of a mental check there, and we know that this is the correct answer. And our previous work ruled out any other possible cases. All right. So we're moving along here quite nicely. Part C. The 4th number in a chain is 1. Determine all possible values of the first number in this chain. Okay. So we're looking for a chain, and it'll go something, 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 1. Okay. So maybe it starts with x, x, and then x2, or we'll call it y. X, then y, then z is equal to, and then we get 1. Okay. So we get these guys, and we want to know what possible values of x could have started this whole thing off. Okay. So there's two ways we can approach this. We can start with x, and unfortunately we don't know a whole lot about x. X can be less than or equal to a half, x could be greater than a half, and that gives us different possibilities about what formula in terms of x we can have for y. And that in turn gives us multiple formulas we can have for z in terms of x. And that'll give us a lot of formulas that we could, in the end, equate to 1 and get x. Another thing we could try and do is say, okay, we got 1, what might z be? What, for the possible values of z, then what might y be? And then from the possible values of y, which there'll probably be a lot of, what might x be? So you can go either way with this. You really can. The nice thing here is that we only have 4 terms in our chain, so we can start with x and write out all the possibilities in a bit of a tree. So if we start over here with x, so we either have 2x put out, or 2 times 1 minus x, but that's really just 2 minus 2x. Okay? So these are our possible values for y. Y could be one of these depending on what x is. Okay? And then, so from this y value, it's possible, whatever it is, we might end up doing 2 times it again. Okay. Just fix that a little bit. Or we might do the same 2 minus double the number sort of thing. So. And what's that? That's going to be 2 minus 4, so that's negative 2 plus 4x. Okay? And these are some of the possible values for z. Okay. Well, what if y had been these values down here? Okay, we could have 2 minus 2 times the input, which is 2x, so that's 2 minus 4x. Or we could just straight up double it again if 2x is still less than or equal to a half. Okay, so these ones here in our third column, these represent our possible z values. Now we're going to get our possible, we'll write them here on this page, values for 1. Okay, so either it's 2 minus double this, so that's negative 2 plus 4x, which is really just 2 minus negative 4 oh geez, so 2 plus 4 minus 8x, which we can just write as 6 minus 8x, so we can erase some of our work here. Okay. Or we could just double this, so that's negative 4 plus 8x. Or we could have 2 minus double 4 is 8, so 2 minus 8, that's negative 8, minus 2 times x, so that's negative 6 plus 8x. Or we could just straight up double this one, 8 minus 8x. So working from the bottom a little bit, we get 8x and then minus 2 minus 8x. And here we have 4 minus 8x. And then this one in here, we have 2 minus twice 2, so that's negative 2, and that'll be plus 8x. Okay? And we could label these. Okay. And in doing it this way, we get a nice little tree just of all things in terms of x. And, well, we understand the machine just a little better. Okay? In the wide realm of possibilities, depending on appropriate values of x and such, we could follow this tree and look at all these possibilities at the end of each one. In each column, the numbers all seem to have this nice little pattern. Starting from, so if we're in the third column, 2 to the power of 3, that's 8. So we're definitely going to have something involving 8x, is something we can notice. How about this constant term? We can notice it goes from 8 all the way down to negative 6, which is negative 8 plus 2. And we hit all the even numbers between. And we notice that we either have plus 8x's or minus 8x's, so we understand the formula a little better. Okay. So how do we get possible values of x? Well, we know these numbers at the end here have to be equal to 1. So what we can do is we can take each one in turn and solve for x. Is that going to do it? No. But it's going to give us all the possible x values, and then we're going to have to go back and check. If we start with this x, here, the first one here, 8x equals 1. So x is 1/8. Now we have to go back and check. Okay, if we start with 1/8 over here, is that really less than a half? Does that really double it? And then do we really have to double it again? And then do we really have to double it again and get this final value? We have to go back with whatever potential x value is and trace it and make sure it actually ends up going through this whole thing. So 2 minus 8x equals 1. Well, that's negative 8x is equal to negative 3. All right. So 3/8, well, yes, that's definitely less than a half. So we double it to 6/8. Okay, now that's more than a half, so we would go up. 2 minus 4 times 3/8, so that's 2 minus 12/8. So that's 1 minus 4/8, so that's going to be a half. And so that definitely goes down into this category here. Uh-oh. We were supposed to go down, down, and then up. So whatever it is, this one's not going to work. Doesn't work. All right. How about this one here? 4 minus 8x equals 1. Okay. So that means that negative 8x is equal to negative 3. Again. Okay. So 3/8. Yep, we definitely double it to 6/8. We go up. Okay, we're on track. That's good. That's what we want. And now from 6/8 we go to a half. A half goes down. So this one works. So we'll give these ones little check marks. How about this one here? So 8x is equal to 1 plus 2. So x is equal to 3/8. Well, 3/8 goes down. It doubles because it's less than a half. Then it goes up. And then it goes down. So this one doesn't work. Alright, so we just continue along with this, and whenever we cross one out, we're going to explain what happens. So this one here, negative 8x equals 1 minus 8. So x is equal to 7/8. Okay, well that definitely goes up to 2 minus 14/8. So that's 2/8. So that definitely goes down. It gets doubled. All right, and then that's 32 minus 28. So that's 4/8. So that's a half. So that definitely works out. How about this one here? This one also is 7/8. So that's a no. Okay. And this one here, well, that's x equal to 5/8. All right. So 5/8. So that's more than a half. So if we start with 5/8 over here, definitely it's following along with the tree. So that's 2 minus 10/8, which is 6/8. So that definitely moves up to here. Okay. So that's 28 minus 2. So that's 4/8. Definitely that's a half. So this one works as well. And this last one here, that's negative 8 is equal to negative 5. Now to get full marks, we need to explain what we're doing. So let's go over here and we're going to write down a little bit of an explanation. So we worked out possible formulas for 1 in terms of x. And as we said, solving these formulas aren't just going to give us the x values. They're just going to give us possible candidates. So what did we do? We had to go back to the start of the tree with our value of x that we thought might work, our candidate value of x, and we checked to ensure that this value and how did we do this? We checked that it matched the end formula based off So at any given moment, was the x value we started with, did it give a y value that then gave a z value that followed the pattern and led to the formula in the end? So we explained a little bit. We've explained all that we were trying to do here, which was just using this tree. We got possible values, possible formulas in terms of x. We equated them to 1. We got candidate values. And then we were able to reject those candidates, like this 5x at the top. Even though 5x turned out to be a value, it wasn't the 5x corresponding to this formula that worked. Okay? You can phrase that however you like. So x equals 1/8, 3/8, 5/8, and 7/8. And the possible values of x, the first number, were exactly what we were asked to prove in this question. Okay, fourth number in a chain is 1. Determine all possible values of the first number in the chain. Now I'm a little disappointed because there was no value, no candidate value of x that wasn't eventually a valid answer. So that suggests that either this part was meant to be easy, or the people who created the question didn't foresee using this particular tree method. Which is fine. Either or, just it's nice when those sorts of things are anticipated. So you do have to really know what you're talking about. Because if you just calculated all those values of x based on the final tree, you would have gotten an 8th, a 3/8, 5/8, and 7/8 in the end. And you wouldn't have had to really discern, as we stopped and did. We tested our candidate values of x. All right. So the last question in the whole contest, question D, for some positive integers m greater than 3, if the first number in the chain is 2 over m, so 2mths, then the 8th number in the chain is also 2mths. Okay, so I'm noticing that they're doing this a lot. So question B, we had the machine put a number in and produce itself. And in part A, we encountered 6/11ths a couple times, and 10/11ths. So it's very much a question of creating cycles is sort of what this machine is doing here. So we get 2mths back, so 2 over m. Determine 3 positive integers m for which this is true. So the phrasing there is kind of odd, and it's got me a little caught. So determine 3 positive integers m. So that suggests to me that there's a whole host of them, and that they might be rather tricky to figure out. Or the question is such that there are only 3 answers, but it's really difficult to prove that these are the only answers. That's just what I'm getting from just the language. Okay. So we have a chain of 8. It starts with 2m and then it ends with 2m. Okay. So unlike this last question, we're probably not going to be able to draw a tree. This is way too long. It's going to take up way too many spaces. And in the end, we're going to get 128 different possible sort of equations. But we can use our work in the last part, in part C, and come up with a little bit of an idea. Okay. So here's our tree from our last part when we did 4, a chain of 4. So we started with x, and this is what the final number might have looked like. Okay? It might have looked like this. Okay? So we could possibly try and generalize this form. Figure out exactly, is it going to be 6 minus 8x, or is it going to be 6 plus 8x? Is it going to be this and that? We could try and come up with a general formula for the possible outcomes after so many iterations of this machine. Okay? But we're just we're a tad stuck because we would need to prove that. Because this is the written portion of the competition, we would actually need to prove, why is it going to be this, why is it going to be that. But one thing we can say for certain, and we could probably reason this out fairly well, is that after a certain number of steps, after 3 steps, it's going to look like some even integer plus or minus 8 times x. That's probably something we could say and we could reasonably say. The reasonably prove. The reason we could probably prove this is no matter what the machine is doing, it is always doubling the input in some manner. It's got a constant, and that changes, and whether or not we're plus or minusing the input, that we can't really say for certain, but we're only ever doubling the input. Okay? So if we start with a value of x, after n steps, our machine outputs some number of the form probably, well, let's just keep it simple. Let's just say some integer k plus or minus, and what do? We have after n steps. Okay, so does the first one count? So after we multiply the machine one time, yeah, there we go. Some number of the form 2, so k plus or minus 2 to the n x. And we're just going to say an integer. If we need to come back and refine things and say k is an even integer, we have the space to do that, just like we went back and refined, and we had a trapezoid in question 2 of part B. Okay. So we claim this. How do we prove it? Okay. Well, we have to use a sort of an induction argument. So it's clearly true after 0 steps because x is equal to 0 plus or minus 2 to the 0 times x. Okay? So clearly our formula works right off the bat. Okay? At step n, what are we doing? We're putting in 2 to the n minus 1x. And we're going to say that that's equal to y, just because we need a name for it. So if y is less than a half, then what do? We output 2y, which is going to be 2k plus or minus 2 to the nx. So it still follows our formula. Fantastic. If y is greater than a half, then what do we output? We output 2 times 1 minus y, which is 2 minus 2y. And we know what 2y is, so it's 2 minus 2k minus plus. The sign here switches. 2n minus x. So really that's just a single number right there. So we'll write that all together. Minus plus 2 to the x. Well, really, the minus plus and the plus minus, they don't really matter. They're the same expression. It's still so by applying the principles of mathematical induction, we have a base case. After 0 steps, our formula holds. And assuming our formula holds after the n minus first step, we show that it then holds at the nth step. So you can also notice that here we have 2k, so that'll definitely be even, and this will also be even. So if we want to go back and say k is an even integer, in fact, let's just say that right now, just in case we need it later on. Okay, I'll stop saying it and I'll just do it. All right. If we need to get more particular with this formula, we may have to refine it a little bit, refine our induction argument, but I think we're okay. But let's see what that gives us. For a chain of 8, what do? We've applied, if we have a chain of 8, the starting number is 0, then we apply it once to get our second number. We apply the machine a second time to get our third number. So how many times do we apply the machine? Okay, so we apply the machine a total of 7 times. So the number that we get out in the end is going to look like some even number plus or minus 2 to the power of 7 times x. So the 8 number looks like k plus or minus 2 to the 7x, which is really just k plus or minus 128x. Okay. But we know that this number is going to be equal to x. So x looks like this. Okay. So now we have possibilities. We can start solving and trying to get a fraction here. That plus or minus makes it very difficult to try and isolate what x is. So, first of all, we start off with this case. Let's assume it's plus. Then we can rearrange and say x minus 128x is equal to k. K is some integer, some even integer, in fact. Okay. So x minus 128x, so that's going to be, oops, not minus 128, it's going to be minus 127. Okay. So x is going to be negative k, so negative of an even integer, over 127. But we know x is supposed to look like 2mths. Okay? So 2mths is what we're looking for. So we have two different fractional expressions. We could try and figure out what m might be in terms of k if there are ratios here. So let's do that. All right, so that tells me that negative km is equal to 2 times 127. And you can probably fiddle this sort of thing out with your calculator. But if you notice, 127 is a very special number. It's prime. So, knowing that it's prime, we can really only conclude that, so either m is going to be 1, 2, 127, or 2 times 127. Okay, whatever that number is. Let's figure out what that is with our calculator. 2 times 127, that's going to be 254. Now m can't be 1 or 2, since m is greater than 3. Okay? So either m is 127 or m is 254. So if m is 254, well, then there's nothing left for k to be other than minus 1 here. So m could be 127. Now we'd have to make sure, we'd have to go through and double check that this all does work out. We do get 2 over 127 eventually gives us 2 over 127 back. So if we check 2 over 127, he goes to 4 over 127, goes to 8 over 127, all of these being less than a half, goes to 16 over 127. So that's 1, 2, 3, 4. We have 4 more to do. 32 over 127. 64 over 127. And now we're over the halfway point. So we're at 6. So we'll have 2 more to do. So 64 over 127. What does that turn out to be? So we're going to have to do 1 minus 64 over 127. So that'll be 128 minus, so we'll get 63 over 127. And we'll have to double that. So that'll be 126 over 127. Just using our calculator. But this too is over a half. So we'll have to do 1 minus 126 over 127, which is 1 over 127, and double that. So m equals 127 works. We found one of the numbers. All right, and that was the only one that came about when we said, what did we say? When we chose plus 128x rather than minus. So we still have another case to work out. X equals k minus 128x. So let's work on that now. K minus 128x. So then bringing this over to the other side, we get 129x equals k. So k is still an even integer. And we know that it's going to look like 2 over m. Okay, and m is still going to be positive. It's got to be greater than 3, in fact. So Km equals 2 times 129. So once again, we make the observation that K is even. It helped us out last time. It narrowed down the choices of M we could make. We can also note that 129 is divisible by 3. We get 3 times 43. Yes, that does work out. Okay. So we can make a little chart here. So K could be 2. It could be 6. It could be 86. That's 2 times 43. Or it could be 2 times 129, which is 258. But it's got to be one of those 4 because K has to be even. Okay? And M has to be positive, so K is also going to be positive. So what does that leave us for M? Well, M could be 129. Sure. M could be 43. M could be 3. Or M could be 1. But both of these won't work because M was said to be greater than 3. So we have only 2 possible values left. M is 43 and M is 129. And since the question asks us for 3 values of M, we're likely done. But this is the written section. So we still have to prove that these are the correct answers and we haven't screwed up anywhere. So these are our candidate values. All right. So we just need to start trying them. 2 over, let's start with 43. 2 over 43, that's going to go over to 4 over 43. And that's going to go over to 8 over 43. We're still less than half. We're looking for something over 21 would do. 16 over 43, well, that's still less than a half, so 32 over 43. So 1, 2, 3, 4, 5, we need 3 more. Now 32, that is over. So we're going to have to use that other formula. 32 43rds is more than a half. So we're going to have to do 1 minus 32 43rds. That gives us 11. So 11 43rds, and then we double it. Okay? And now that's still over a half. So we double it. Or sorry, we do 1 minus that. So 43 minus 22. That's going to be 21. So 22 43rds, and then we double that. So 42 over 43. And when we work that one out, 1 minus this is going to be 1 over 43. We double that, we get 2 over 43. So that one works. And now we just have one more to figure out 2 over 129. So that goes to 4 over 129. We double for a lot of these at the start, I'm noticing. Oops, 32 over 129. 64 over 129. Now that's still less than a half. So we got one more to do that before it tips over. 128 over 129. Well, that's 1, 2, 3, 4, 5, 6, 7. And when we do the next one, we can do it in our heads or we can do it by calculator. We get 2 over 129. So only 3 values of m work, but that's okay. We were only asked for 3. So we had 127, 43, and 129. And if we check, we have a chain of 8. Well, we were able to work out chains of 8. We were able to actually show that these ones work. And we determined 3 positive integers m greater than 3. You'll notice they threw in the greater than 3 because in part B we figured out that if it's just 2 over 3, then we just keep getting 2 over 3, 2 over 3, so that would trivially be true. So greater than 3 positive integers, 127, 43, 129. These are in fact the only ones that work. And that concludes the contest. So hopefully you've been able to glean a little bit. You got to try these questions on your own. Math is not a spectator sport, as a great mathematician I know once said. So you really should be trying these ahead of time before you watch these videos. But hopefully, my solutions, my way of thinking, my methods have shown you a little bit of insight. And hopefully, with question 3 and question 2 on this contest in particular, I've shown you don't always go in knowing exactly how to do the questions. You have to tinker around a little bit. We were just fiddling around with a tree in part C. We came up with a guess at a general formula in D. We didn't even know if that was going to help us solve the question. It could have been a completely different way we needed to attack D. I don't even know what the solutions say. But, you can watch these videos. You can go on the Cimc website. Just Google Cimc, and you can find find their solutions, or you can try and make your own. But hopefully you've enjoyed the 2012 Cimc Cimc competition, and hopefully you'll join me for another contest on another day.